This is Lab 6, Faraday's Law for Ben Skalka. Starting with the introduction and purpose. The purpose of this lab is to observe and measure an instance of current being created in a tube with a moving magnet, an example of Faraday's Law. This experimental model was then recreated computationally and compared to determine the difference in results between our experimental model and what we expect to happen. Fundamental physics principles. The fundamental principles used in this lab are Faraday's law, Biot-Savart law, Newton's second and third laws, the magnetic force and flux equations, including Ohm's law, and you can see them all listed there. First look at the results. Our experimental average time was 1.64 seconds, and our computational estimate with our previous lab mu was 3.06 seconds. Starting with the experimental model. In this model, we assume that air resistance was negligible, the bar magnet was a dipole, aluminum foil had typical conductivity as a solid tube, and we considered the system to be the magnet in the tube while surroundings were everything else around it. The initial conditions had the magnet held above the top of the tube while the tube was held 1 foot in the air. The magnet was dropped and recorded 5 times, and the average time to transverse the tube was recorded. You can see the data there, and the average tube time was 1.64 seconds. With the computational model, it was recreated computationally using Python in GlowScript. The magnet was modeled as a dipole, and we used the mu value of 7.26 created in Lab 3 to model it. The dimensions of the tube listed beside were also input into the code. Code then calculated the magnetic field and flux of the dipole as it moves. Continuing with the computational model, this code shows the iterative loop where it calculated the induced current in each section of the tube as well as the magnetic force applied as the magnet fell, then calculated the motion of the magnet, and then printed the predicted time to drop. Initially in the computational model, we used the value of the magnetic dipole mu. We calculated mu to be 7.26. However, with this value, the predicted results differed vastly from the experimental observations. With the results of the computational model, after researching the magnet and previous groups' calculations of its magnetic dipole strength, we concluded our initial calculation was incorrect. We tried to estimate the correct mu by adjusting the strength of the dipole until the model bore results similar to the experimental observations. This estimated corrected mu value was 5.3. However, due to air resistance, the true value may be even lower. Moving on to the discussion, the intensity of the coloring on the tube indicates the magnitude of the current flowing through each ring. Red and blue indicate current flowing in opposite directions, so which color represents clockwise and which is counterclockwise? Well, red is counterclockwise and blue is clockwise as viewed from above. What happens to the dynamics of the system when you flip the magnet around? Well, nothing would change about our results, but the orientation and direction of the magnetic field and induced current would flip, but it all cancels out to be the same. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? Well, it tells us that the force of gravity is sharply opposed by the magnetic force as velocity slows down and holds constant. And then the force of gravity again affects velocity as the magnet leaves the tube and is no longer affected by upwards force. So it changes throughout the motion. Moving on to what if. What if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? If this were true, hypothetically, then the induced current would increase and thus magnetic force would increase. This would lead to the magnet falling through the tube slower. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? Well, there would be less conductive material, which would lead to a decrease or disruption in the induced current, and this would decrease the magnetic force. This would lead to the magnet falling much faster. Possible sources of error. This experiment had a few sources of error. One is human error in calculating the dipole strength. In Lab 3, which we already talked about, human error in the analysis of the video to determine experimental falling time, just, eyesight and the difficulties in trying to make it exact. Possible unaccounted discrepancy between conductivity of wrapped aluminum foil versus solid tube conductivity in computational model. And lastly, discrepancies in height between each drop, so initial velocity in terms of how much time it actually has to reach the bottom. And that is the end of the lab.